Welcome back, Physics 11, to another exciting episode of Physics Notes with Mr. Wellsby. So today we're going to be introducing you, or rather reintroducing you, to the topic of forces. Now, so far we have studied kinematics. So kinematics is the study of the way things move, how things move. But now we want to learn why things move the way that they do. So we're taking it to the next level of that kind of abstraction. So we learned about how, but not really why they move. And in this unit, we are going to be exploring why objects move. And that reason is forces. And so this right here is the study of dynamics. So the study of why objects move that way, this is what's called dynamics. Okay, so what is a force? Now, a definition you may have heard in the past is a force is a push or a pull. And that actually sums it up quite well. If we think about all the examples of forces you may come to mind when you think of that word, it's probably they all involve some sort of push or some sort of pull. And the unit of force is what's called the Newton. Now remember that it's named after a person, but despite that, we don't capitalize the unit, so it's still a lowercase unit when we're spelling out the word, but the symbol for the unit is going to be a capital M because it's named after someone. Now, in the universe, there are four main forces, and you've probably heard of a few of these, but probably not all of them, or likely not all of them. So those four main forces are gravity, and then we have the electromagnetic force, and lastly, we have two forces that we don't really experience on a daily basis, but they're involved with interactions between particles in a nucleus or in an atom. And so those two forces are what are called the strong force and the weak force. And both of these are related to atoms, or really the nucleus of atoms. The weak is what kind of controls nuclear decay. And the strong force is the force that keeps protons and neutrons together. So if you think about it, we know that positive charges will repel positive charges, or like charges repel, opposite charges attract. So if you've ever wondered how inside the nucleus, you've got all these protons that are basically touching each other, when really they would, from the electromagnetic force, they should want to repel each other, but somehow they hold themselves together. That's because of the strong force. And so you can see that at least in those very, very small distances, the strong force is much weaker or much stronger than the electromagnetic force. Now, if you want, pause the video here and try and think of all of the forces that you may be familiar with, see what names of forces you can come up with. And if you don't want to pause the video, that's fine too. I'll just give you a list of some of the more common ones and ones that we're going to be dealing with. So, whenever we're talking about a force, we're always going to use the capital F to indicate it's a force. But then we're going to put a lowercase or a subscript letter, and that letter indicates what type of force it is. So all of these F's are types of forces, and the subscript is going to be just some sort of, gives you an idea of what force that we're referring to. So Fg is gravity. This is also known as weight. So it's another name for the force of gravity is weight. We have Fa, so this is some sort of applied force, like if you're pushing or pulling on an object. You might think of air resistance. F is the force of friction. We'll be dealing with that one quite a bit. Then we can talk about normal force, and we'll talk about more detail about what that is in our next few lessons. But the normal force is a force that always applies whenever two solid objects are in contact with each other. And there's a few other ones. We have Ft or Fe. These are tension tension force, or elastic force. So these are some of the common ones. We might have other ones that come up. Buoyancy might be another one, but we're not going to deal with that one ourselves in Physics 11. Okay, so force of gravity. Force of gravity is force between two objects that have, and really any two objects that have mass will create a gravitational force. So I've got a gravitational force attracting me to my laptop currently. When you're in class, you'll have an attractive force between each of your students, between each of you, right? So all of you apply a gravitational force to everything else around you, but it's just way too small to really put into, be able to sense that directly. The force between any two objects, mass, and mass is measured in kilograms, and one way of defining that would be essentially the amount of matter. So that is our mass. Our weight, which is measured in newtons, this is just another word for force of gravity. Okay, and one thing to think about is how these change depending on where you are in the universe. So think about if you're here and suddenly you were teleported to the moon, which of these two would remain the same and which of these two would be different. So hopefully you can see that the amount of matter that you have is going to be a constant. So if I were to be teleported to the moon, the amount of Mr. Wellsby that exists would be the exact same. I would still have two arms, two legs, a head, a torso, etc. And so that's not going to change. So the mass is going to be constant throughout the universe, but your weight does vary, or weight varies depending on where you are. So if you're on the moon, the force of gravity on you would be less, and that's because the moon's mass is much less. And so if you have two smaller objects, then the force of gravity between those two objects will be smaller. You may remember this from an earlier year, but in case you don't, the force of gravity, the formula for it is Fg equals m times g. So m is our mass, and g is the gravitational field strength. This is also known as the acceleration due to gravity. And how you describe it really depends on the context. So we'll go into more detail later on with that, but both of these are completely acceptable definitions for G. It has a value of 9.8 meters per second squared. So if we think about what we've learned from acceleration, what this is essentially saying is that if you, ignoring air resistance, if you start to, let's say you jump out of a plane with your parachute on, uh, when you first jump out of the plane, your initial velocity is going to be 0. But every single second, your velocity will increase by 9.8 meters per second. So what that means is after 1 second, you'll be going 9.8 meters per second, 19.6, 29.4, etc., etc. So every single second, you're going to be going 9.8 meters per second faster. That's what g being 9.8 meters per second squared means. Also, just a good exercise, see if you can determine what the units for g are going to be. So one of the units that we have is we can say it's 9.8 meters per second squared, and that is a completely valid way of looking at g. That ties in with the idea listed here, that it's the acceleration due to gravity. But if we rearrange this formula, if we have Fg equals m times g, if we rearrange that, then we have g equals Fg divided by m, and so this is measured in newtons per kilogram. So newtons per kilogram is another perfectly valid way of describing what g is. And what this tells us is that for every kilogram of mass, there's going to be a gravitational force of 9.8 newtons acting on that when we're close to the surface of the Earth. So just another way of looking at that. It's the same thing. So 9.8 meters per second squared is kind of when we're thinking about it in terms of acceleration, which is mostly what we'll be doing in physics 11. And then 9.8 newtons per kilogram is something when we're thinking about how strong the gravitational field is around the Earth. And this is more for grade 12. But we can still think of it this way. Okay, so let's try this out. So G does vary depending on a few things. So in terms of a planet, this G varies depending on the mass of a planet and the radius of a planet. So the further out you are from something, the less the force of gravity is going to be. So on Earth, we already know this is going to be 9.8, and these are all in meters per second squared. On the Moon, it's around 1.6. On Jupiter, 26. On the Sun, 274. So what this would mean is every kilogram of mass that's close to the surface of the Sun is going to experience a force of 274 newtons pulling it down, which is obviously much, much greater than what we have on Earth. So let's try this out for yourself. You can put your own mass in here, or you can choose another mass. My mass is around 68 kilograms. So you can try and calculate that out. You can ignore this part in there. That's a UK measurement, the stone of 14 pounds. So if my mass was 68 kilograms, see if you can figure out what my force of gravity or my weight would be on Earth, and also see if you can figure out what my weight would be if I was on the Moon or on Jupiter. So pause the video here and see if you can calculate. If you only know your weight in pounds, you can do a conversion for yourself there as well. So pause the video and see if you can complete these calculations for your own mass or for my mass if you'd like. So it should be straightforward if you've already tried this out. Hopefully you have. So if I want to know my weight on Earth, we know that Fg is going to be my mass times gravity, so 68 times 9.8. If it's on the Moon, it's going to be this 1.6 times 9.8. And if it's on Jupiter, it's going to be 26 times 9.8. And in these three examples here, my weight would be, let's see, 68 times 9.8 gives me 666. If I'm on the Moon, my weight would only be, whoops, that should be times 68. Sorry, that was my mistake here. So 1.6 times 9 times 68 and 1.26 times 68. This is I reversed the order. This is going to be M is the 68 and G is the 1.6. Either way, the two answers there are going to be 109 and 1,768. So in all three of these cases, that would be my weight on these various locations. So that's it, short video. I hope you learned something, and as always, please let me know if you have any questions. Thank you.